Imagine holding a palm-sized obsidian disc that once captured a face by firelight. Then jump to a gold-petaled space mirror reading galaxies at dawn. Between those two reflections lies a story of secrets, poisons, and breakthroughs. Guilds guarding recipes, chemists silvering glass, engineers teaching light to obey. In minutes, we'll sprint across 8 millennia to see how mirrors stopped merely copying us and started expanding how far and who we can see. Meet the person who quietly invented the mirror you use every morning, Justus von Liebig, a 19th century German chemist. Raised above his father's pigment shop, Liebig fell in love with the practical magic of materials, then trained in Paris under Gay-Lussac. In 1835, he published a deceptively simple method for silvering glass, using a chemical reducer to deposit a thin, brilliant layer of metallic silver onto a perfectly flat pane. Suddenly, mirrors could be bright, consistent, and, crucially, made without the toxic tin-mercury amalgams that had dominated Europe for centuries. Liebig wasn't chasing luxury. He was solving a materials problem, and the solution slipped into daily life. To see why this mattered, zoom out. For generations, Venice guarded glassmaking secrets on Murano like state intelligence, while France built its own royal manufactory to break the monopoly and line the Hall of Mirrors at Versailles. Those feats proved demand, but the process remained costly and risky. Liebig's chemistry unlocked scale and safety. Glass sheets could be mass-produced, silvered, protected, and shipped worldwide. That's the pivot point in our story. From here, mirrors stop being rare trophies and become infrastructure, on walls, in instruments, inside telescopes, setting the stage for the leaps that follow.
The story begins with stones and metals. Around 8 millennia ago, people in Anatolia polished obsidian, volcanic glass, into palm-sized discs that returned a ghostly, firelit face. Centuries later, artisans in Egypt and Mesopotamia, then across Greece, Rome, and China, refined copper and bronze mirrors. These were heavy and required constant polishing, but they were durable, affordable status objects. Technically, they worked by creating an ultra-smooth metal surface. The smoother the polish, the sharper the image. Glass enters early, but tentatively. Roman sources mention glass mirrors backed with metal, and scattered finds suggest experiments by the 1st to 2nd centuries CE. The idea was elegant. Use clear glass as a perfectly flat window and lay a bright metal behind it, so the reflection appears protected and crisp. The challenge was execution. Ancient glass had bubbles and color. Metal backings were uneven. For a long time, the metal mirror remained the practical choice. The breakthrough of the late Middle Ages and Renaissance came from Venice, especially Murano, where glassmakers invented cristallo, exceptionally clear glass, and paired it with the tin-mercury amalgam technique. Craftsmen spread tin foil on a flat table, poured mercury to form a gleaming amalgam, then pressed a glass plate onto it and slid away the excess. The result? Brilliant, relatively flat mirrors that dazzled Europe. The cost was steep, both in money and in health. Mercury vapor poisoned workers, but the radiance of a large, nearly flawless mirror was irresistible to courts and merchants.
State power soon joined the reflection race. In 1665, France founded a royal glass works that would become Saint-Gobain, specifically to break Venice's monopoly. Investment in cast plate glass technology made larger sheets possible. The triumph was architectural. The Hall of Mirrors at Versailles, 1678-1684. It wasn't only decoration, it was a message. Mirrors had crossed from personal grooming into public spectacle, signaling that controlling light and the image meant controlling taste,
commerce, even diplomacy. The modern household mirror dates to 1835, when German chemist Justus von Liebig published a reliable process for silvering glass. Using a chemical reducer, he deposited a microscopically thin, uniform layer of metallic silver onto meticulously clean glass. The method produced brighter, more consistent mirrors without mercury's hazards. Because it scaled well, it democratized reflection. Mirrors left palaces and entered homes, shops, and scientific instruments. Science pushed mirrors even further. 19th-century astronomers replaced tarnish-prone speculum metal telescope mirrors with silvered glass, lighter, easier to figure, and better reflecting. In the 1930s, researchers learned to evaporate aluminum in a vacuum onto glass, forming hard, durable front surface coatings that resisted tarnish. This single material shift unlocked larger, more reliable reflectors, setting the template for modern observatories. Meanwhile, industry solved flatness and cost. In 1959, the float glass process sent a continuous ribbon of molten glass across a bath of molten tin. Gravity and surface tension leveled the sheet perfectly. Polishing and grinding largely vanished. Suddenly, high-quality glass became cheaper and more consistent, and silvering lines could churn out mirrors for bathrooms, elevators, storefronts, and skylines. Coatings grew sophisticated. Dielectric stacks, alternating nanometer-thin layers of materials with different refractive indices, created mirrors tuned to specific wavelengths, perfect for lasers and scientific optics. Electrochromic rear-view mirrors arrived in cars, automatically dimming on command to cut glare. At microscopic scales, MEMS micromirrors steered light digitally for projectors and instruments. At cosmic scales, segmented and actively aligned mirrors clad in precious metals for infrared sensitivity unfolded in space. From hand-polished stone to machine-polished segments orchestrated by computers, the through line is clear. Every leap improves smoothness, size, efficiency, safety, or spectral control, and each one widened what mirrors could do beyond simply returning our face.
The first shock is how political mirrors became. Venice's Murano guilds guarded cristallo and tin mercury methods like state secrets, threatening defectors. France responded by luring artisans, founding a royal glassworks, and crowning the effort with Versailles' Hall of Mirrors. Reflection wasn't luxury, it was soft power, broadcast in glass. The second is the price of brilliance. Tin mercury mirrors dazzled because mercury wets tin into a gleaming amalgam, but vapors poisoned workshops. Centuries later, museum conservators still treat old plates with caution. Liebig's silvering wasn't just prettier, it was a health revolution that made large-scale safe mirrors thinkable. A third twist, mirrors quietly bent art and perception. Jan van Eyck's convex mirror in the Arnolfini portrait expanded space inside a painting, while 18th-century tourists carried Claude glasses, dark convex mirrors that pre-filtered landscapes into picturesque scenes, an analog Instagram, shaping what viewers believed looked right. Finally, astronomy pivots the whole story. Speculum metal telescope mirrors were heavy, dim, and tarnished fast. Silvered glass, then vacuum-deposited aluminum flipped the script. Lighter, brighter, maintainable optics that could scale. That single material's turn opened the door to giant reflectors and eventually to segmented computer-aligned mirrors that will define what comes next. Today's everyday mirror is quite high-tech. Float glass, made perfectly flat on molten tin, then silvered or aluminized and sealed behind primers and paints so humidity can't creep in. Cars add electrochromic layers that tint against glare. Buildings use selective coatings to reflect heat while passing daylight. In labs and devices, mirrors get specialized. Dielectric stacks for lasers, hot-cold mirrors to manage infrared, and deformable mirrors that flex thousands of times per second so telescopes can cancel atmospheric blur in real time. Shrink the scale and mirrors become machines.
MEMS micromirrors, millions of hinged tiles, steer light for projectors, 3D scanning, and even some LIDR units. At the other extreme, space telescopes use segmented, actively controlled primaries that fold for launch and phase up into a single optical surface in orbit. The theme is the same as ever: tighter control over where each photon goes. What's next? Expect smarter consumer mirrors with better, longer-lasting electrochromics and subtle AR overlays. In optics, metasurface and ENZ-style coatings promise ultra-thin mirrors that tailor color, polarization, and phase on a pixel-like grid. Astronomy will push bigger segmented mirrors on the ground, paired with laser guide stars and more cryogenic, gold-like coatings in space. The mirror of the future may look nothing like glass, just patterned nanofilms that make light behave on command. From a hand-polished obsidian disc catching a flicker of firelight to a gold-petaled mirror unfolding in space, the arc isn't just about brighter images, it's about widening what counts as a mirror. Each leap, Venetian cristallo, Liebig silvering, vacuum-deposited aluminum, float glass, dielectric stacks, deformable optics, pushed reflection from vanity to vision, from bathrooms to boardrooms to the edges of the observable universe. Along the way, mirrors shaped taste and politics, fueled new kinds of art, and turned starlight into data we could reason about. And now we're on the edge again. Micromirrors that switch like pixels, nanofilms that sculpt color and phase, windows that adapt to sun and privacy, telescopes that self-correct the sky. If a mirror is anything that precisely returns or reorders light, what will it look like 50 years from now? A pane of glass? A cloud of MEMS? A wafer of metasurface? Or something we haven't named yet? If any moment stuck with you, the hush of an obsidian disc, the glitter of Venetian halls, or a space mirror unfolding, tell me which era hit hardest and why. If you're curious where this series should go next, drop a topic: the rise of lenses, the story of prisms, or how adaptive optics fights the atmosphere. If you enjoyed time traveling through everyday tech, there's a library of deep dives waiting. Pick another and keep exploring. And if you know someone who'd love this journey, feel free to pass it along. Your ideas shape what we build here next.